Okay, guys, we're going to be going over both of the sections from chapter 22 that we just started. So when I assigned 632 to 643, that is two sections, which I had you do. So let's take some good notes. We're going to be doing some work with this, so we want to have a good picture of what we need to know. So we started out in this section talking about electromagnetic waves. So they consist of electric and magnetic fields, and they vibrate at right angles to each other, and that is an important thing to remember. So if we could visualize them, clearly we can't see them. You'll notice the magnetic field is in purple going across here, and the electric field is moving up and down. So they kind of are perpendicular to themselves, to each other, I should say, and they're traveling towards the left in this case. So you can see the direction of travel is there. So the electromagnetic waves are made by those vibrating electric and magnetic fields. So that's what it would look like if you could see it. So electric fields are surrounding just about every charged object, and that's important to note. And obviously magnetic fields are surrounded, magnets are surrounded by them. So you produce what are called electromagnetic waves, and that is the particles vibrating of those electrically charged particles. And we'll talk about the spectrum too, but these waves produce radiation. So any type of electromagnetic wave is going to give off radiation, and some amounts are minimal and some are a little more heavily giving off radiation. So we all know that we need to mention the difference between the speed of light and the speed of sound. So the speed of light is about 300 million meters per second, and it's about 880,000 times faster than sound. So a few weeks ago we were talking about lightning and thunder, right? And we kind of talked about that idea of you see the lightning bolt even though the thunder happens almost simultaneously. It's a result of lightning, but it's right, right after. But it seems so much farther. It seems so much more delayed, right? Because the speed of light, right? The lightning hits you, right? Your eye, you see it, but the speed of sound is so much slower that it takes a few minutes to get or a few seconds to get to your ear. So this is just a visual of it, right? So basically, we don't really know of anything that travels faster than light at this point. So it is very, very fast. And so sometimes a great example of this, besides lightning and thunder, would be, if you're really far away from someone in an open area like a gym, or if you're looking down the street at somebody shutting a car door, you see them shut the car door, but it almost is like a bad movie where there's a delay in speaking or sound, and you hear it a split second later or a couple seconds later sometimes. So that's another example of the differences between it. It does happen at the same time pretty much, but it's taking longer to get to your ear. So it takes about 8.3 minutes for light to travel from the sun to the earth. That's kind of interesting to think about. So the light that we're seeing was, there's a delay there, right? That's pretty interesting to think about too. So the Earth is 150 million kilometers away from the sun. So think about that. Even though light travels fast, that's 8.3 minutes is a long time. So electromagnetic waves from the sun are a major source of the energy here on the Earth, right? They help photosynthesis, and fossil fuels store it. So it's really, really important. So that's kind of the basics of electromagnetic spectrum and the waves. Now we're going to break down the spectrum a little bit more. So the second part that you guys read about is about the spectrum specifically, and you guys watched a video last week too about that. So what are they? They're all those frequencies or wavelengths of electromagnetic radiation. So what I did was, this is the picture out of your book, and I kind of copy and pasted it together. A couple of things you need to take note of. On this side has the least amount of radiation, okay? So we start with radio waves, we go all the way up to gamma rays, which we'll talk about. Up here you see this purple arrow, so it says the electromagnetic spectrum is arranged from long, so the wavelengths are really long on the left. Moving to the right, the wavelengths get shorter, okay? So long to short wavelengths, but when we talk about frequency, it goes from low to high, so it's the opposite. Make sure you understand that. That is a big piece of importance, okay? So we start out with long wavelengths and they get really short, and we start out with low frequency and it gets really high as you move to the right. So we'll talk about each type of wave here, but remember too that the radiation from radio waves, which are like televisions and radios and stuff like that, are going to be a lot less. The radiation is going to be a lot less than right over here when you get to the gamma rays, okay? So radiation, we know, is not something that's good for your body. It's something that in, amounts as you go through life minimally isn't a big deal, but if you're exposing yourself to a ton of radiation a lot, it's not good. So when we first talk about the electromagnetic spectrum, radio waves are at the very beginning. So we need to talk about how radio signals are broadcast. So it's not something that I bet you guys take a whole lot of time to think about. It just shows up on your radio. But we know there's AM and FM, so we'll talk about that too. So the radio station basically turns sound into an electric current. So the current produces radio waves and they send them out from the antennas that you see kind of around Madison. So the radio receives it and converts it into an electric current, and then we convert it to sound. So obviously you can't hear radio waves, but they carry energy that gets converted into sound. So we have AM radio, which is kind of grainy at times, we say. It has longer wavelengths and it can bounce off the atmosphere and travel farther. So AM stations come in a kind of a wider amount of area or space. FM gets less affected by electrical noise, so it sounds a lot better. It's not as grainy. So that's kind of the difference, but they're different frequencies. TV signals are also carried by radio waves. So we tune into a specific television station, and that's a specific frequency, right? So most TV stations are using radio waves, but they have shorter wavelengths and higher frequency than what a radio station would be using. Now we have to talk about microwaves. So they are kind of next as far as we move across the spectrum. How do they cook your food? Well, there's a magnetron, which is the device up here, talk about letter A, and that produces the microwaves. It accelerates charged particles inside. And then those microwaves reflect off this fan and they go into the cooking chamber, right? So then they can go several centimeters into your food, and the energy of those microwaves cause the water molecule. So any type of liquid pretty much that's in your food causes them to kind of move and rotate, and it causes the temperature of your food to heat up. So it was a great invention that makes our food get cooked a lot faster than on the stove. Some say not as well, but most people use microwaves. So we use microwaves in radar, right? Where you've heard of radar being used might be like with a police officer who might be trying to tell how fast your parent's car is moving. So the radar gun sends out microwaves and they bounce off the car and return to the gun. And so at that time, it calculates the speed of the car and lets the police officer know if the car was going too fast. So that's another way we use microwaves. Then we have infrared waves. The sun is not the only source of infrared rays. Everything gives them off, right? So there is obviously a temperature thing going on there. So the hotter something is, the more infrared rays it has. So we use infrared binoculars to see things that give off heat at night. Sometimes you'll see people looking for, an animal or sensing a person if we're looking for someone, if someone's missing, right? You see that on TV stations, but that's how that works. They can sense hot spots in the woods and things like that. Then we have visible light, right? The Roy G. Biv that you learned when you were little, the color scheme, right? Red, orange, yellow, and so on and so forth. So they're the only ones we can see. And so we can see those different wavelengths of visible light as different colors on the color scheme, right? So water droplets can separate and you can see the little picture there of the rainbow. But it's a narrow range of wavelengths. And so it's right in the middle of the spectrum pretty much. And so there it is. So the colors of the rainbow. And then we have UV light, right, that comes from the sun that can also be good for us, right, in a lot of ways. It helps us absorb vitamin D, kills bacteria in food. That's why you'll see lights on food at restaurants sometimes. But it radiates our skin, and so it can manipulate our DNA and cause things like cancer. So we want to make sure that we're protecting our body against the sun if we're going to be in the sun for any extended amount of time. And then we have X-rays and gamma rays. When you go to the doctor's office, maybe you go to the dentist, maybe you hurt your arm and you have to get an X-ray, they'll many times put a lead vest on you because you don't want to radiate or get an X-ray on organs that don't need it. It's okay to get an X-ray if you need one, right, at the dentist or whatnot, but you don't want to get them when you don't need them and too often because, again, it's radiation that your body doesn't need. So the gamma rays, which are used in extreme situations, are the most penetrating. Usually when you go in to have radiation for cancer, they only radiate the cancerous cells, right? So they target the radiation where it's supposed to go on the tumor or the bad spot and save your other cells, hopefully. So it's a gamma rays or radiation is good because it helps us cure cancer and things like that. But it also, in a way, causes it if we expose our bodies to it in certain situations. It can be a cause, not the only cause of cancer. So that is the electromagnetic spectrum. And just to kind of look back at the spectrum again, and we can look at it in different ways on the videos that we've seen. But there's that visible spectrum right in the middle that we can see, the visible light that we can see. So these are just some examples of where we would use the different types of waves for different things in our lives. So that is it. Make sure you rewatch if you need to write anything down or grab something that you missed. Feel free to do that.